So my name is Okan Yılmaz. I'm a researcher in ArcelorMittal Research and Development Ghent, which is a steel producer, some of you may know. And maybe you heard there's another name that we go by, the Flemish acronym for Research Institute in Steel called OCAS. So as the title says, I'm gonna describe you a method that we use to assess the fatigue life of cold-formed ultra-high strength steel sections. So just a quick word about our R&D operation. It's distributed all over the world, and it's in total like 1,500, nearly 1,500 researchers. And in the Ghent branch that I'm working on, it is around 150. So, generally, we of course are active in different types of portfolios, what I'm working on mostly is what we call industry grades. So of course there's maybe a boring but a very logical reason why people want to use high strength steels, because they simply give you better static, not always linear, but still better fatigue properties. And of course, when you say high strength steels, okay, you can think of different things. So what I am specifically talking about is what we call high strength low alloy steels. And the material that we used for this study is S700MC. So which is a thermomechanical hot rolled grade that guarantees you over 700 megapascal of yield strength. In general, they are used in the application of heavy machinery. And what I mean is such as telescopic cranes, tippers, agricultural machinery, truck chassis, and etc. And of course, once you increase your strength levels, then you can just do the same design, maybe for higher load capacities. You can reduce your weight, and etc. But the story is maybe a bit different when it comes to fatigue. And for that, the application I will focus on is telescopic crane booms. So these crane booms are, the profiles are manufactured via cold forming. And then, of course, we have to weld it both to the structure and the weld to complete the profile. The welds themselves are also, let's say, a point that you have to assess the fatigue, but the focus on this presentation will be the cracking on the cold form profiles. So then it gives the customer some flexibility to make designs with variable bending angles, bending ratio, and also different surface states, which all change the fatigue performance. And the response will be rather complicated because during forming, you are gonna generate macroplasticity in the part. You are going to generate residual stresses, so that it's not very certain immediately how your product will really perform. And in addition, the fatigue performance can be hindered by, if you consider low bending ratios or high bending angles in your designs, then it will increase the stress concentration factor. Or maybe the bending equipment that you're using is poor condition, then it will create surface with defects. Then once you form them, it's going to be it's going to affect the in-use properties. And maybe you have poor material, the material we are selling, maybe it has a suboptimal quality in the flat state. And this will enhance defects with bending. So that's, of course, what we don't want. So what we want is sort of a quality assessment. So we want to be sure about the material that we are selling to the customer. So in order to assess how it's going to perform in fatigue, what we do is we bend flat sections, weld them together, and then form a closed profile, and then test this under constant amplitude conditions. So once you do the test, and if you do the analysis, you'll see that the stress state with the bend profile and the failure location where the cracking happens is representative of the application. So in these profiles, like under loading, if you have failure in the band section, what you end up is cracking starting with the inner radius and then propagating to the full thickness of the material. And with the once you do the test, what we are doing is that we check the test displacement And then with checking this, it's possible to study the initiation and the propagation cycles. So you will see that as the cycles go by, there's a certain limit that your stiffness loss will ramp up, and ramp up. So we have a practical limit of 0.1 millimeter that we say that, okay, at this point, we have a crack initiated. And then if it is 1 millimeter, the displacement has increased. We say that, okay, the crack is propagated enough. So that's how we come up with the initiation and propagation cycles once we make the test runs. So our objective is to use this method to qualify our material concepts for cold form fatigue so that we can fine-tune our products for the customers that requires these applications, and also maybe support them to their design and testing processes, because what they do in general is that they do more expensive prototype tests with the full crane boom, which is hard to do, expensive to do, and with the lower scale component tests, if you have extra info from them, then it's really educated for them to really select what they will test for their prototypes. So then what we did is first banded the 700 MC with different bending ratios. So if you check the EN standard, you will see that for 700 MC, there is a bending ratio limit R/T equal to 1. So that you shouldn't go below it. So if you go below, then you're gonna create defects in your bend profile. It's gonna be too rough, so that it's not really suited. For this study, we deliberately bended below the recommended bending ratio to generate these defective surfaces, because we also would like to get an idea how if they're gonna underperform, and they should underperform, how it's gonna be, and then how it's gonna affect our, let's say, quality assessment. So if we start with some tests, and then do the constant amplitude test at a certain maximum force, then what you can end up with at different bending ratios is, of course, as you go down in the R/T, then you're gonna end up with lower lives. Okay, this is expected, maybe a bit boring, but what's really interesting to see is if these points are really overperformed or underperformed. So if the material is really a good fit, and then the expected life was, for example, 10,000 K, but it really overperformed. So this is rather more interesting to see. And for that, of course, we have to have a calculation. So that's this is a base that we can calculate the experimental performance. And to calculate the fatigue initiation life, we are using the FKM guideline. This is an association in Germany. It's called the Research Institute for Mechanical Engineering. I'm not going to attempt to pronounce the German name, but it provides a practical method using local strain approach. What we do to come up with a component Euler curve is we do some linear elastic finite element simulation using Neuber method to approximate the plastic strains and stresses. Then we can calculate the damage parameter, add additional factors, and then come up with a curve that is specific to the component that we are considering. There is a certain damage parameter which is called PRAM. This is based on Smith-Wesson Topper approach. This is simply a multiplication of your stress amplitude and strain amplitude with the Young's modulus, and then you take a square root. So you take into account both of them. And there is a certain K parameter which takes the mean stress effects. I mean, there are more equations, but due to time constraints, it's not very smart to like really go in detail to put some numbers. Just it's important to know that this is also a function of the ultimate tensile strength. And then you can come up with a certain curve, again with two different knee points, which are also functions of ultimate tensile strength. And once we construct the curve, then we can put our points with the calculation. So at the first glance, it was interesting to see that the R over T 0.5 was really below the calculations. And maybe it is better to see these results on a cross-check graph. So now I'm comparing the experiments and calculations on a scatter band with a factor of 2. And then what I can do is I can define some unsafe and safe regions. So this is essentially design space. And it was nice to see that already a good separator is happening for the R over T 0.5, because remember, these were the band faces with defects, so we expect them to underperform. Once we load, then there should be immediately some crack should start, and then it shouldn't be only the stress concentration factor, but also the initial crack should hinder the fatigue performance. So if we add the compressive stresses, so we had also some runs with shot peening and grinding that result in longer fatigue lives. But what we haven't done, but we plan to do, is the addition of the residual stresses. So since they're not added yet, simply they are like shifted on the right more into the safe side. But of course, if you include the residual stresses in your linear elastic analysis, then it will be possible to get a better calculation so that they will be also close to the approximating line. So these calculations can really benefit from the inclusion of residual stresses. And if I do the same with, not with the banding ratio, but smooth bands and defective bands, now the use of the unsafe and safe regions are more clear. And if I just check how these cracks look like, so the crack propagation direction is always from top to the bottom. So, yeah, here you see the material behind, so that you should just ignore this part. What we see with the defective bands are, first, there's a rough patch, shows the initial defect propagating the first cycles. And we can even hear that in the test. Once we start the test, there's like this click, and then, but the load is not that high, so it's still that the material can collect itself, and then you can get smoother fatigue crack. And if it's a good band, if it's a smooth band, then you have only the, you can clearly see the initiations, and then you have a nice smooth fatigue crack surface. So by including the stress concentration effects and approximating flow curve, it gave us a useful separator in quality assessment of our material. So this will be the main conclusion that I would like to highlight. And also just to remind that the test methodology itself can reproduce the effects of bending and surface parameters. Now we are extending this with to consider different materials and surface treatment effects. And what I see is that the residual stresses would be necessary to include as an input, because with the different materials, you will have different limits. You'll have different reactions to the forming, and especially the calculations at high fatigue lives could really benefit from the inclusion of residual stresses. So if there are any questions, I would be really happy to take them. Thanks.